Now that we've talked about these otherwise known as simple gas laws, I thought it'd be interesting for you to just see if you can work some of these problems. So this is just going to be a problem set. Alright, so the first example is a Boyle's law. If a sample of helium gas has a volume of 120 milliliters and a pressure of 850 millimeters of mercury, what is the new volume if the pressure is changed to 425 millimeters of mercury? So for this set, put me on hold for a minute, set up your problem, take inventory, get your Boyle's law formula, rearrange it to solve for what you need to, see if you can work it, and then after you've worked it and got an answer, then come back, start me up again, and we'll work it together. So if you have worked this on your own, welcome back, and so I'm going to work this for you. So in this particular problem, we're going to take inventory, and what we see is that the volume 1 is 120 milliliters. P1 is 850 millimeters of mercury. It wants to know what V2 is, so I just usually put a question mark. If the pressure is changed to 425 millimeters of mercury. So notice we can use these formulas, including the combined gas formula, for any of these where the situation changes, where you change from an initial condition to another type of condition. So this is our inventory. And so now let's look at the formula. You remember the formula for Boyle's law is P1V1 over, or P1V1 equals P2V2. Now we know the combined gas law at this point. So what I'm going to do is I'm going to write the combined gas law, my pig's vomit over trough law. Don't laugh at me. Okay. All right. And so I'm only looking at P and V. Okay, so I'm only looking at P and V. So the reason I wrote the combined gas law is I'm just saying that's the only really one you have to remember. And so P1V1, the temperature's not mentioned, so I can just scratch that out. And so now I've got P1V1 equals P2V2. I'm going to solve for V2, so I have to get it by itself. So in order to do that, I'm going to have to divide both sides by P2. So I'm going to divide this side by P2 and that side by P2. And so then that gives me V2 equals P1V1 over P2. Alright, so that's my formula. So then I'm just going to plug and play. V2 equals P1, which is 120 milliliters, times 850 millimeters of mercury. Almost didn't leave myself enough room, divided by P2, which is 425 millimeters of mercury. Millimeters of mercury will cancel if I don't go up a page. They will cancel, and they will leave me with milliliters, which is what I want. So V2 is going to be 120 times 850 divided by 425, and you should have gotten 240 milliliters. Okay, so that's Boyle's law. Charles' law, and again I'm going to take inventory. So I've got V1 equals 420 milliliters. T1 equals 18 degrees C. I'm looking for T2, and it tells me it wants it in degrees C. You got to watch it. Sometimes the test will tell you that. And if I'm going to change the volume to 640 milliliters, notice that P and N are constant. So my P1V1 over T1 equals P2V2 over T2. So I'm not worried about P this time, so I'll just do that out. So V1 over T1 equals P2 over T2. Now, this is where I want to show you something. if you're solving for T and it's on the bottom, sometimes people get confused when they have to rearrange the equation. So I want to introduce you to something in math I affectionately call flip it. So the rule in math is that if I've got two things that are equal, so on each side of the equal sign, and I do something to one of them, I can do anything as long as I do the same thing to the other side. All right, so what I'm going to do is I'm going to flip it. So instead of V1 over T1, I'm going to say T1 over V1 equals T2 over V2. And then the reason I'm doing that is because then I'm solving for what's on top, and it's just a little bit easier intuitively to do that. And so I'm solving for T2, so I'm going to have to get rid of V2. So I'm going to have to multiply both sides by V2 because that'll cancel it on this side. What I do to one side, I must do to the other. So V2. So that leaves me with T2, because these V2s cancel, equals T1 V2 over V1. And just a little tip, whenever you're doing this, just remember that whatever you're doing over here is what's going to change on the other side. Whatever you originally had on this side is going to stay the same. So don't change that. Just you're going to be multiplying or dividing by something that was on the other side when you're getting rid of something. Okay? So just keep that in mind. You're not going to change whatever side you're is not the one you're trying to get by itself. It's going to stay the same. You're just going to multiply or divide by something that was on the side with the one you're wanting to solve for. Hope that makes sense. Okay, so I want to call your attention to one other thing. When we talk about temperature and gas laws, we talk about them in absolute temperature. Okay, so notice that I have this in degrees C. And if you recall, I've got to change that to Kelvin. And in order to do that, I have to add that to 273, and that's going to give me 291 Kelvin. And if I don't change it to Kelvin, I'm going to get the wrong answer. All right, so now I'm going to solve for my T2. So T2 is equal to T1 in Kelvin, so 291. And so let's put asterisks by the things we have to change. All right, 291 times V2, which is 640, that's Kelvin, sorry, divided by V1, which is 420. The most often error made is getting these mixed up, these volumes, for some reason. I don't know. Anyway, so T2 ends up being 443 Kelvin. Okay, yay, I have an answer. Well, I do, but it's not the answer that the question asked for, because the question wants the in degrees C. So I've got to do what I did at the beginning, T2 equals 443, but this time I've got to subtract 273. And so the answer that the test would be looking for is going to be 170 degrees C. And you know how mean I can be. I might have that number on there, 443 degrees C, and you see that number and you're like, yay. No, make sure you pay attention, okay, and get that in the right one. And you can't go directly using degrees C and get degrees C. Remember that you must convert to Kelvin, and if it wants it in degrees C, you must convert it back. That's the thing to remember about these temperature ones. All right, the Gay-Lussac. Again, pause me. I should have told you that on the other one. Pause me and try to work it, all right, and then come back and see if you got it right, okay? All right, so in this problem, P1 is, whoop, that was crazy. All right, P1 is 645 torr. T1 is 128 degrees C. And I know I'm going to have to do what? Convert that to Kelvin. And that's going to give me 401 Kelvin. T2 is what I'm looking for when I change the pressure to 824 torr. Torr and millimeters of mercury are the same, by the way, if you recall from the very first. All right, so you got 401 Kelvin, you got 645 torr, you got 824 torr. And as long as they're all the same units, you're good, as long as temperature's in Kelvin. All right, so if you don't remember the Gay-Lussac or combined gas law or whatever we're doing, oh, oops. Sorry about that. I should have been doing it on this one. Darn it. Here. I don't want to start over. I'm just going to erase, okay? Bear with me. Sorry. Alright, I'm erasing. You can just use this time to check your answer, right? Okay, sorry. Alright, now, Gay-Lussac. Alright, so we said P1. I'm having a bad time. This is what happened to me last time too, isn't it? Alright, P1 is 645 torr. And T1 was 128 plus 273, which was 401K. Wow, retirement program. T2 is what we're looking for if the pressure is 824. All right, so we using the combined gas law, we know P1 V1 over T1 equals P2 V2 over T2. So this time we don't have any V's, so we can scratch those out. And so P1 over T1 equals P2 over T2. We're solving for T2, so we can flip. T1 over P1 equals T2 over P2. And we're going to solve for T2, so we multiply both sides by P2. All right, and so those will cancel, and so that will give me T2 equals T1 P2 over P1. And then I can plug and play because I've got Kelvin temperature and I've got torr and torr. Okay, so T2 equals T1, which is 401K, times P2, 824 torr, divided by P1, which is 645 torr. And so T2 is going to be 512 Kelvin. And if I want that in degrees C, which I believe it did say in degrees C, 512 minus 273 is going to give me 239 degrees Celsius. All right, sorry about that confusion earlier. Okay, so the last one is where we're going to use the actual combined gas law to do a combined gas law problem. And so in this one, we're going to have all kinds of numbers. We're going to have everything. We're only going to be missing one thing. So we have a sample of helium gas, which has a volume of 0.180 liters, a pressure of 0.8 atmospheres, and a temperature of 29 degrees C. At what temperature will the helium have a volume of 90 milliliters and a pressure of 3.20 atmospheres? Okay, now we really have to take inventory on this, and what I'm going to look at is I'm going to make sure that I've got all the same units, because I need all the same units before I can plug them in. Now I've got liters and I've got milliliters and I've got atmospheres and I've got atmospheres and I've got temperature. So I have to change every one of these just about, right? Okay, so the first one I know how to do this because I've been doing it for a while. 29 plus 273 is going to give me 302K. All right, now let's look at volume. Volume, I got 0.180 liters and 90 milliliters. I don't have to change them both. I just have to change one of them so that they both have the same units. So I'm going to change that one, and you can do either one. And so there are 1,000 milliliters, if you recall, in 1 liter. So that's going to give me 180 milliliters. So now my milliliters and milliliters match. That's 180. All right, then I've got pressure, and I've got one pressure in atmospheres, and I've got another pressure in atmospheres. So those are actually okay. Sometimes they will be different, but I've got atmospheres and atmospheres. All right, so now I've got all the same units. So now I'm good. So now I'm going to go over here and I'm going to say, all right, my pigs vomit over troughs. Now, which one am I solving for? I'm solving for T2. T2. So I've got to get T2 by itself. So first thing I'm going to do is I'm going to flip it. So T1 over P1V1 equals T2 over P2 V2. Since I need to solve for that, I've got to multiply both sides by this, so I can cancel that. So I'm going to multiply over here P2 V2, and so that's going to give me T2 equals T1 P2 V2 over P1 V1. See, got to be super careful with these because a lot of times it's easy to get ones and twos mixed up. All right, so now since I took the time at the beginning to get everything in the right units, then now I can plug and play. So I just go over and I say, all right, I got 302K for T1. All right, and then I've got for P2, I've got 3.20 atmospheres. And then for V2, I've got 108. Oh, nope. See, that's why I'm checking myself. V2 is 90 milliliters. And then I'm going to divide by P1, which is 0.8 atmospheres, times V1, which is 180 milliliters. Now, make sure that you pay very close attention to your math on this. All right, and so when I have multiple things to multiply and divide, what I typically do is I divide everything, I multiply everything on the top and everything on the bottom. So when I do that for this problem, I get 86,976 divided by 144. And then I don't make a mistake with my parentheses and all that. So I get a T2 of 604K. And I can go back and I can say atmospheres, atmospheres, milliliters, milliliters, K is my unit. And it, of course, wants it in degrees C because we're in America. So T2 equals, well, I guess even if you're in Europe, you could get it in C. 604 minus 273. In degrees C, it's going to be 331. That is your answer. So it saves you a lot of work and time to go ahead and make sure that your inventory is correct, and that is that they're all in the right units and or the same units, that you got Kelvin temperature in there before you work the problem. Hope this helps.